class. Today's lesson, the learning outcome will be to describe the motion of a charged particle in the presence of both magnetic and electric field, where the V, the B and E are perpendicular to each other. This is class by Raj, teaching for Physics, STPM, Semester 2. Okay, so the most important thing about this is to understand the concept. The first concept is when an electron enters a perpendicular into a uniform electric field, the electron will experience an electric force, and this electron will travel in a parabolic path. So if you see in this diagram, a concept of projectile motion or parabolic path is used to determine the various quantity of the motion. Now, for the next concept, when a charged particle enters with a velocity perpendicular into a uniform magnetic field, the particle will move in a circular motion. The path will be a circular path. And when it is a circular path, you have to apply circular concept, where the magnetic force is equivalent to the centripetal force and is always directed towards the center of the circle. Now, the question here for today's lesson is, what is the path of a charged particle in the presence of both electric and magnetic field? If the charged particle enters at the same time in the presence of both electric and magnetic field, what will be the path of the charged particle? Let's look at the lesson. Now, to study the concept, we need to look at the example. So, we are going to take an example of a cathode ray tube. A cathode ray tube is a vacuum tube containing one or more electron guns, the beam of which are manipulated to display image on a fluorescent screen. Now, cathode ray tube are divided into three parts: electron gun, deflection system, and also a fluorescent screen. We are going to look at a simpler version of cathode ray tube in the next lesson. The cathode ray tube is another example. We know our concept, so now we want to apply our concept in an application which is in a cathode ray tube. Okay, cathode ray is actually fast, very fast moving electron, accelerating electron. Okay, now what is a cathode ray tube? I think everybody is very familiar with this. This is a simple cathode ray tube. A cathode ray tube is a vacuum tube, okay, containing an electric gun, okay, and a fluorescent screen, okay, which is to accelerate and deflect the electron beam, which is the cathode ray, okay, and hit on the fluorescent screen to create images in the form of light. Okay, so this is what a cathode ray is. All right, okay. Now let's look at each component here. The first one is the cathode. Okay, so here is a cathode, which is a negatively charged electron. Negatively charged electrode. Okay, so you have many electrons here. Okay, so what happens in cathode is thermonic emission happens. The first process is thermonic emission. Okay, thermonic emissions. Okay, so what is thermonic emission class? Thermonic emission is the emission of electron, okay, is the emission of electrons from a heated metal surface, from a heated metal surface. Okay, so metal are heated here. Okay, metal are heated, which is the cathode, are heated at a very high temperature. Okay, it is heated at a very high temperature. Okay,
And some of the free electrons, okay, will gain a sufficient energy, okay, they will gain sufficient energy, okay, to escape from the metal. So this is what happens in this process here. It is a thermonic emission. Okay, thermonic emission. Okay, next, the electrons are already being emitted. Okay, they are already emitted here, the electrons. And you realize here now, the cathode is also connected to the anode by a very, very high voltage. Okay, high voltage supply. So now the electrons are already emitted. So the electrons will absorb, because this is connected to a very high voltage supply, the electron will be given, okay, electric potential energy. Electric potential energy. They'll be supplied with electric potential energy. The electron will absorb the electric potential energy and convert it to kinetic energy. Convert to kinetic energy. So what happens here is that E watt is equals to half mv squared. Okay, E watt equals to half mv squared. So once when the electron is been given by electric potential energy and convert it to kinetic energy, so they will start to accelerate very fast. So they are already free electron which is accelerating very fast. So they called cathode ray, or we call it as electron beam. So they will accelerate very fast and pass through this here. So this is anode. Okay, anode we have two. We have focusing anode and we also have accelerating anode. Okay, we have what? We have focusing anode and we also have accelerating anode. Okay, so if you see in this diagram, this is the one that is part is accelerating and this one is the part that it is focusing. So all the electrons are focused into one beam. All the electrons are focused into one beam and then given electric potential energy and accelerate very fast towards the next part. Okay, next component. So now we are having free electrons. We have electrons here. Okay, coming with a velocity v. Alright, they enter into the second component here. Okay, once when the free electron enter into this next component, what will happen to the free electron? Okay, let's look at here. Now what is in the second component is, we have an electric field. This is the positive, this is the negative. We have an electric field. So this is the direction of the E. Okay, so this is the E. And then we also have a magnetic field. Okay, so this is the magnetic field. Okay, so if this is the magnetic field into the page and the electric field is in this direction from the positive to the negative, then we say they are perpendicular to each other. So the magnetic field is B. Okay, so now let's look at one by one. So when this is the positive, this is the positive, this is the negative, 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 negative. When the electron enters into the region of electric field, the electron will be exerted by a force. Will be experience a force. Okay, what force? Electric force. Okay, which is F E equals to Q E. Now how to know the direction of the electric force? is by looking at the charge. So this is a negative, it will be attracted to the positive charge. Okay, so this is negative, it will be attracted to the positive charge. That is, therefore, we will realize here that here we have the electric force which is directed towards the positive. Okay, which is upward. It is direct towards the positive, which is upward. Okay, alright, so this is the electron, so it will be directed upward. Okay, then if we look at the separate and we look at the magnetic field, this is the magnetic field. Okay, and this is the electron. Okay, what will happen? Now, definitely the electron will experience a force. What force? Magnetic force. Okay, what is the force? Is a vector. How to know the magnetic force? The magnitude. The magnitude is Fm is equals to BQV. How to know the direction? By using the Fleming left hand rule. Okay, so if I use here Fleming left hand rule, okay, so this is the electron, so I use F equals to negative EB times cross product V. Okay, EB cross product with B. Okay, so BV cross product lah. Okay, so then we do what? We use our Fleming, we use our left hand. So the FBV. Okay, FBV because it's a charge, moving charge. So B is into the page. Okay, V is here. So it's upward. So since this is upward, negative of upward will be downward. So the direction is downward. Okay, alright, so the direction is downward, this one will be upward. So when both exist together, so we'll have two forces there. One is upward, one is downward. Okay, now next, what shall we know? What shall we look at? Okay, what happens? Okay, here, in this place here, yeah, I'm going to just, okay, maybe here. If Fe is greater than Fm, what happens? If Fe is greater than Fm, the electron will go into a path of, will follow the path of a parabolic. So it will follow this path. Okay? Alright. But if Fm is greater than Fe, what will happen? The electron will follow this path and perform circular motion. Okay? But if Fe is same as Fm, what will happen? The electron will straight, it will move straight. So for the electron to move straight, Fe must equals to Fm, and electron will move straight. Okay, it will move straight and hit on the screen. It will hit on the screen. So in order for that, Fe must be equals to Fm. So what is Fe? Fe is QE. What is Fm? BQV. So therefore V is equals to E over B. So the velocity of the electron must be adjusted so that the electric field must be divided with the magnetic field. Okay. Now how do we adjust the V? We adjust the V by adjusting the accelerating potential. Okay. By adjusting what? The accelerating potential. Okay. Alright, so then only the electron will move straight and then will hit on the screen. Okay? Alright. Thank you, class.
The next example to understand the concept is the mass spectrometer. A mass spectrometer is used to measure the mass of an ionized atom. It is also able to separate the ions of the different isotope of an element according to the mass to charge ratio.
At the next application, which is a Bainbridge mass spectrometer. Okay, Bainbridge mass spectrometer. meter. Okay, what is the use of a Bainbridge mass spectrometer? Is to measure the mass of an ionized atom. Is to measure the mass of an ionized atom. And also it is to separate the ions. Okay, it separate the ions of the different isotopes of an element. Okay, according to the mass. To charge ratio. Okay, all right, ratio. All right. Okay, so here these are Bainbridge mass spectrometers. So here we have a source of a positive ion. This is called as a ionization chamber. Ionization chamber. Now this chamber is used, okay, is used to ionize the gas. Okay, it's used to ionize the gas whose mass or isotope is to be determined. And positive ions are produced. Okay, so this is an ionization chamber. So now when the positive ion, okay, now what is a positive ion? Okay, positive ion, if one or more electrons are removed from the atom, then it has a net positive charge and it becomes a positive ion. So now we have a positive ion which comes here, which flows here in the collimator slits. Okay, alright, so now the positive ion will enter into this region here. Okay, it will enter into this region here. Now what is this region here? This is a velocity selector. This region is a velocity selector. It's a combination of electric and magnetic field. So you see here we have electric. Okay, we have electric and we also have a magnetic field. Okay, alright, and they are perpendicular to each other. Okay, so if this is the one of the magnetic field, this is the electric field, so they are perpendicular to each other, and only ions with the selected velocity are able to pass through. Okay, so only ions with the selected velocity are able to pass through. Okay, let's talk about what actually happens inside the velocity selector. Okay, inside the velocity selector, okay, now the ion pass through. First thing what will happen to the ion is it will be exerted by an electric force. Okay, it will be exerted by what? By an electric force. So this is the negative, this is the positive. So this is the ion. Okay, so it will be exerted by an electric force. So the direction will be towards negative because it's a positive ion. So the direction will be towards negative. So the direction of the electric force will be in this direction, Fe. Okay, alright. Then you have a magnetic field. So what will happen? The ion will be exerted by the magnetic field and will be exerted by a magnetic force. Okay, because it is exerted by a magnetic field, so it will be exerted by a magnetic force. So what will be the direction of the magnetic force? The direction of the magnetic force is using Fleming left hand rule. So you use a Fleming left hand rule. So this will be the positive ion. Okay, so it will be F equals to QB cross product BV. Okay, so FBV. So the V, the B is here, the V is here. So the direction of the magnetic force will be in this direction. So that's why you get here in this direction. Okay, so that's why you have here Fm, you have here Fe. Fe is due to the electric field, Fm is due to the magnetic field. Okay, if Fe is same as Fm, what will happen? The positive ion will move straight. Okay, they will move straight. The ions will move straight. So in order for this to happen is QE equals to BQV. So V is equals to E over B. Okay, so they move straight. If Fe is greater than Fm, what will happen? The positive ion will move in this direction. Okay, it will perform a parabolic path. The path will be a parabolic, so it will move in this. But if Fm is greater than Fe, then what will happen? The positive ion will move in this direction, which is the concept of a circular motion, circular path. Okay, so now the ions are moved straight because the Fe is equals to Fm. Now when the ion moves straight, okay, what will happen is it will neither be deflected, so it will move straight, and then it comes into the second region here. In this second region, we have all this magnetic field. Okay, we have all magnetic field only. So what will happen to the ion? What will happen to the ion? The ion will only be exerted by a magnetic force. Okay, so what will be the direction of the magnetic force? We use our Fleming left hand rule. So this is the B, this is the V, this is the V, this is the B. So the direction of the magnetic force will be in this direction. Okay, and the concept is, since it's a magnetic, it will follow a circular path. It will follow a circular path. So it goes and hit on the photographic plate and leave mark on it. Okay, from the place where it leave mark and hit on the photographic plate, and then from here is the diameter. So from here to here is the radius of the semicircular path. Okay, so inside here what happens, the concept is, okay, here is a uniform magnetic field B. Okay, so here Fm is equals to QVB. Okay, and circular path, that means it is Fm is equals to Fc. So QVB is equals to mv square over r. Okay, so m over q is equals to rvb over v square, which is rb over v. Okay, and the v is from here, the v is E over B. So we substitute v equals to E over B. So we get what? M over Q is equals to RB square over E. So therefore the mass of the ionized atom will be M equals to RB square EQ. Okay, so in order to that, we know that we keep all the constant in one side. So B square Q over E times with R. Okay, so that is how Bainbridge mass spectrometer is used to measure the mass of an ionized atom. Okay, so B is constant, Q is constant, E is constant. So different mass will give you different radius. So that's why you have different radius for different mass of an ionized atom. Okay, all right.
Now, let's look at another example of a spectrometer, where this spectrometer we are going to learn how to determine Q over M for a positively charged particle.
We have another type of spectrometer, okay, where this type of spectrometer is used to determine the specific charge Q over M. Okay, specific charge Q over M for of a positive ion, okay, another type of spectrometer. Alright, so in this spectrometer class, alright, what is the first thing? Now let's look at this part here. Okay, so number one, inside here. Now inside number one is a material that we want to investigate. Okay, material that to be investigated. Okay, material to be investigated. Okay, so usually it's in the form of a gas or vapor at a very low pressure. Okay, at low pressure. Okay, so inside this W here we have a material that we want to investigate. So they are in the form of gas or vapor and they are at a low pressure. Then what happened is, process number 2 is here. Okay, so you can see that this is a cathode and this is an anode. So that means a beam of fast electron from the cathode collide with this material. Okay, so this is a beam of a fast electron. Okay, a beam of a fast electron. Okay, so the beam of a fast electron produced from this will collide into the material that we want to investigate. Okay, so once it collide, what will happen is positive ions are formed. Okay, so what will happen is some of the material will ionize. Okay, and we will have positive ions. Okay, now this positive ion are drawn out from W. It is drawn out from here because now this is a positive ion, right? So the positive ion are drawn out because Y here is an electrode with a bit slightly negative respect to X. Slightly negative respect to X. So here is a positive and this one is slightly negative. So what will happen is the positive charge ion will start to draw out from the from this place here, from this W here. So it will start to draw out. Okay. Now when it's drawn out, you can see here we have a voltage. Okay, between electrode Y and Z, there's a voltage. So what can we say? We can say that the ions will be accelerated. Ions are accelerated. Okay, by much greater potential difference. Greater potential difference. Okay, so you see here is a potential difference between electrode Y and Z. That means electric potential energy is given to the positive charge. Electric potential energy is given to the positive charge. Positive charge convert electric potential energy to kinetic energy and then it will accelerate. The ion will accelerate with a very high velocity v. So it will accelerate and comes out in this part here. Okay, now when it goes into this region, okay, into this region number 5, what happens? Okay, so this region, you can see that this region is, we have magnetic field. Okay, we have magnetic field in this region. Okay, alright, we have magnetic field. So the ion, the positive ion that comes out, enters into a region that has a magnetic field. So what will happen to the positive ion? The positive ion will be exerted by a magnetic force. So we use our Fleming left hand rule here. So the B is out of the page. Okay, so the B is out of the page. Alright, so the V is here. Okay, FBV, right? So the B is out of the page, the V is here. The direction of the V is here. So therefore, the direction of the force, magnetic force, is in this direction. And we know the concept is the path of the charge will be a circular path. So you realize here this is a circular path in the magnetic field. Okay. So now what will happen when once it goes into here, it will go through a circular path. So therefore we know the concept of circular motion is also applied in this region here. Okay, in order for the charge, all right, in order for the positive charge to pass through this slit S2 and slit S3, there is a condition where we have to make sure the ion pass through slit S2 and S3. What will happen is we have to control our potential difference V here. We control our potential difference V here. We adjust it until this micrometer shows a non-zero reading. So once when we adjust this voltage, this potential difference here, until micrometer shows a non-zero reading, then this positive ion will pass through slit S2 and slit S3. It will just go with a beautiful circle here. Okay, now when it enters into this region, the concept will be the magnetic force. Okay, it's a circular. So the centripetal force Fc will be equals to the magnetic force. Fc is equals to Fm. Okay, so I'm going to write here with black pen. Fc is equals to Fm. And Fc is mv square over r. So I'm going to use the r here, which is capital R. And I'm going to put here a vector to show that it is velocity. And Fm is bqv. Okay, is also a velocity. Alright, so from this, what can I get is that QB, okay, QB is equals to mv over r. So I'm going to put a v here, a vector here, because I want you all to differentiate. Later I want to differentiate between the v of a potential difference and the v of a velocity. Okay, alright, so here we get QB equals to mv over r. Alright, now we apply back this concept here, which is QV equals to half mv square. Okay, so from here, from this concept here, QV, okay, equals to half mv square. So therefore, V square equals to 2QV over m, big V. Okay, and then V is equals to 2QV over m square root. Okay, alright, so here I'm going to find Q over m. I'm going to substitute this inside here. So it is m over r. I'm going to substitute that. It will be 2Q over m. Okay, alright, so what I'm going to do is I'm going to remove this square root here. So what I'm going to do is I'm going to square everything. So I'm going to square this q square m square, okay, equals to m Okay, wait, I already brought M here, right? So you don't have an M there. Okay, sorry for that. All right, wait, let me see. Q over M, B. Where's my B? B. I forgot my B here. Okay, all right. So wait, R, B square root of 2Q. Okay, so there's no M there. Okay, now hold on. I do properly here. Okay, so look here. Q over M equals to 1 over RB. Okay, I'm just going to write down here like that. So now I'm going to square. So Q square over M square equals to 1R square B square. So here will be 2QV over M. Correct? So then I bring and cancel this Q, this M. So I get Q over M equals to 2B R square B square. Okay? I get that. Q over M equals to 2V. V is a potential difference. Potential difference divided by R square times with B square. Okay, so the reason of this video is to find the specific charge Qm of a positive ion. So we can find the specific charge of Q over M of a positive ion. Okay, all right, take note here. Yeah, so Q over M will be BV over R. All right, correct. Okay, so that's all, class. So you realize or not, the diagram changes, but the concept is still the same for all those examples that we have done for today's lesson. All right, okay, that's it. Thank you, class.